Thank you. Thank you for the opportunity. It's called member seminar, but in some sense it's like a colloquium because it addresses the whole community of the institute. So I thought I chose a topic that has topology and combinatorics and geometry to address, to have something for everybody. But inside there's also complex analysis and algebra. So I think something for everybody. First I'll do some words of introduction, then the historical, some history, not the whole history. And then I concentrate on graphs versus fundamental groups when we talk about topology versus fundamental combinatorics. And then the motivation to all this work from algebraic geometry and a proof of the fun conjecture. And if time allows me, I'll go to the appendices. And the proof is to follow what was suggested here, that every talk has to have one proof at least. Because someone said here, if there's no one proof in a talk, it's like a movie without a love scene. So we will get to the proof. What is the question of topology versus combinatorics for line arrangement? As always, versus could make two questions, whether topology induces combinatorics and whether combinatorics induces topology. It's not could be two questions, could be both questions. And when we talk about combinatorics, I talk about a lattice. The incidence lattice of a line arrangement is the partially ordered set of the intersection of this line arrangement. So we have, and we add, let me take a bigger picture, and we take also like the empty set, which is included in all the points, then including some lines, etc. And for example, you see here that P2 is a triple point, the three lines meet in P2, and you see here that P2, there are three lines going from P2 to L2, L3, and L5. And as I said, we add R2 and the empty set, so we have a full lattice. When we talk about topology, we talk about fundamental group of the complement of the line arrangement. So the question is whether lattice induces fundamental group and whether fundamental group induces the lattice. When I start with the history of the topology versus combinatorics, it started before it was about combinatoric fundamental group versus the lattice. It was related questions. So already in 1980, we have the result of Orlik and Solomon that lattice induces the cohomology group. Goreski McPherson talked about lattice and homology group in very, very general case that includes it also, the previous result. And then when in 1989, Orlik proved that if you have a smooth deformation of the line arrangements such that the lattice and every time the lattice is constant, then you have diffeomorphism. And this relates to R, to the reals, to the complex, to the affine, to the projective, but you cannot move from one to another. It's everything within the real, everything within the complex, etc. in his result. The issue of complex versus real is usually very dangerous. One has to be careful. For example, if I look at that line arrangement, so if I look at it over the real, then the lattices are different because one has a 5 gone while the other one doesn't have a 5 gone. Here we have a 5 gone, this one, and here we don't have a 5 gone. But over the complex, there is a one parameter smooth isotopy on the lattice, a family. There is a family that in a smooth isotopic way moves from one arrangement to another arrangement. So here we have the two parallel line, another two parallel line, and this is the diagonal line that moves from here to here when t equals 0 or 1. Of course, the family goes through very complex lines when it moves from 0 to 1. And because there is this smooth family, the fundamental group are isomorphic as a result of as a consequence of the result I just quoted from 1809. On the other direction, Zhang and Yao proved, Stefan Yao, that homomorphism induces the lattice. This is in the complex case. But the original question about fundamental group and lattice is still remains open. But it was solved. The fundamental group induces the lattice was solved negatively with a counterexample by Falk in 1993. And the example is this example, these two arrangements of 6 lines each. One has a line that connects the two multiple points. One has a line that connects the two multiple points, and one doesn't. This is actually the smallest possible examples in C and in R of this phenomena. So we are left with whether the lattice induces the fundamental group. We have the following results, and it goes slowly. You add one line. It's a big news in the community when one line is added. So at 1997, Fan proved that up to 6 complex lines, the lattice determines the fundamental group of the complement. Then we generalized it to 8 lines, but only 8 lines that are defined over the real. Then up to 8 line over complex line, any line, was done later by 2010. And then Fai, in his thesis, he's from Chicago. He had 2 theses, one in Chicago and one in China. He proved that up to 9 complex line, the lattice determines the fundamental group of the complement. The first counterexample that we have is by Rybnikov. It was announced in 1998 and only published in 2011. So it took some time to publish, and it's not because there were mistakes there that need to be taken care. He simply left mathematics. And in 1998, when it was announced, he was supposed to come to a conference about fundamental group that I organized in Oberwolfach, and that was very nice. It was just to be one of the first lectures, and he never showed up. And I never heard from him and never saw him till September. And in September, I gave a talk in Moscow. And then I said that there is a result which is announced in 1998. So I never saw it published, but I trust it. So someone raised his hand from the back. He said it was published. So apparently it was Rybnikov coming back to mathematics after 13 years out of mathematics. And he has this very complex example. And anyhow, so far, no one found another example before that. But the question, what is the smallest example in terms of number of lines, still exists. So as of now, it's between 10 and 13. So about 10, Fai, that proved the 9 case in his thesis, is now a postdoc at my university, and we are working on the 10 lines. 10 lines, it's much more complicated because this is the first time that the modular space has more connected components than you anticipate. So of course, it gives a chance if there are many connected components of the modular space that we'll find a counterexample there. But still, it's not clear. But anyhow, the modular space of the arrangement is being studied. In the meantime, work was done on characterization of fundamental groups related to different properties, other properties, not only lattice, not lattice versus fundamental group, but different properties. So one important result about nice intersection lattices with special property was done in 1994, and then a shorter proof was just later, just now in October, by Bogomolov-Kulikov. And then about simple intersection lattice, there's also a result. and special properties of the arrangement, other special property of the arrangement, and then also works on special property of the graph. The graph of the arrangement, I will define it in a moment, but the special properties that were worked on in 1997, Fan proved that if there is no cycle in the graph, then the fundamental group has a special property. And in 2009, we proved the reverse to this, to his character. So now it's a characterization, not only a property. And then different other properties of graphs. We also have in regard of graphs two other results, one concerning conic line arrangement, not only line arrangement, and one concerning when the dual of the line arrangement is simple. So what do we have in graphs versus fundamental group? The graph of a line arrangement lies on the arrangement itself. The vertices are only the multiple point with multiplicity greater than 3. And the edges are the segments between the different multiple points on the line, which pass through more than one multiple point. If two lines occur to meet in a simple point, we ignore it. So we only look on the multiple points and the lines between them. These are different examples. These are when you have three multiple points on a line. That usually induces some problem. Here you have also, but you also have a closed triangle. And these are other examples that even though they look similar, they might be very different types of fundamental group.
Is there a reason for those without intuition? Why you ignore the simple points when you draw the graph? Why is the graph enough to capture
The simple points induces on the fundamental group commutative relations, very simple relations. So there's nothing to, they don't contribute much to the structure of the group.
If you have three triple points on a line, what is the graph?
This is the graph, the three triple points and the line between them. It is the graph. It just, for certain reasons, we don't want this example, because then the fundamental group will not be so easy to attract. You will see in a moment.
So,
but this is still the graph.
So the graph has three vertices and two edges?
It has two edges. The case of no cycles, that's what Fan proved in 1997. We say that a graph contains a cycle of length k if there are k multiple points of the graph, each of them more than 3, and there is an edge between two consecutive points and between the first and the last point. So it's closed circle. But here we don't want 3 points on the same line. So what we had before, it doesn't make it a cycle. These are two examples of cycle. Here is a cycle of length 4, and here is a cycle of length 3, but the graph has another edge. This graph is only one cycle. This is a cycle and an edge. So Fan proved that in that case, if the graph has no cycles, then the fundamental group of the complement in the projective space, projective plane, is sum of free group and one commutative free group, and the sizes of these free groups are also determined by the graph. So the mi minus 1, mi is the multiplicity of the multiple intersection, and L is the total number of the lines. And he conjectured that the converse is also true. And we proved in 2010 that the converse is actually, it's also true. So we start from a structure of a group. The group has that structure, and we showed that there are no cycles in that group. So this is one case related to the graph. The second case related to the graph is the case of disjoint union of cycles. So we do have cycles, but they don't intersect each other. And then the fundamental group of the complement has a conjugation-free geometric presentation. A conjugation-free geometric presentation of a fundamental group is a presentation when the natural topological generators, it means every line in the fundamental group has some kind of a generator around it. Very simple generator, just goes around this line and comes back and doesn't touch all the others generators and also does not touch each other, the lines. So these very natural topological generators, the only relations that we have with them is this type of relations, that it's like a cyclic relation. And x here, it's this order, and then we start from this order, and xik jumps to the end, etc. And there are no conjugations on these generators. This is conjugation-free geometric presentation. These kind of presentations are very good because the lattice determines the fundamental group for them, and also one can read the presentation directly from the arrangement. No, this is now does not, the xi, x1 to xn doesn't connect to the intersection of the points. It connects to the line. Every line meets, let's say, the line, some faraway line or line in infinity, and there you go around this line. So it connects to the number of lines and not to the number of the multiplicities. So
total number of lines. If lines do not pass through multiple points, we still count them.
yes, everybody, all lines. The only relations that you have in conjugation-free geometric presentation is relation of this type, where you have like a cyclic relation that goes around and there are no conjugation, and these are geometric presentation. These are geometric generators.
For which sequences I1 to ik do you write these relations?
Well, especially I wanted to say that I wanted to make an algebraic definition. This is algebraic definition of the fundamental group. But I know that usually this goes to connects to the lines that meet in one point, even if there are only two lines. If there are only two lines meet in one point, that will be a commutative relation. But it holds like that. And the disjoint cycle case is to prove that I think that I already put the theorem, yeah. That if it has a union of disjoint cycles, then the fundamental group has a geometric-free, a conjugation-free geometric presentation. And the disjoint cycle case, to prove it, you first do the one cycle case, which apparently is more difficult than you would imagine to start with. And there we use the Braid monodromy techniques, but then to put it together, we use the theorem of Oka from 78, that if you have two fundamental groups of line arrangements that intersect only in few points, then the fundamental group of the complement of union is the sum of the fundamental group of each of them. And the cycle intersecting the vertex is now work in progress. And there's also some explicit result in this case. When we have a 6-line arrangement where there is one cycle of length 3, then the fundamental group is the semi-direct product of ff2 and z times z squared. There are arrangements that have no conjugation-free geometric presentation. For example, the Cheva arrangement doesn't have such a presentation. And this was proven with software that takes two groups and try to see that one group has some type of a subgroup and the other one doesn't have some type of a subgroup. So the proof that I know so far for this is that it was only using the computer. And then the fundamental group is known for this. It looks like a very simple example, a triangle and lines that come from these triangles. But nevertheless, one couldn't prove it. The third case is the case of disjoint union of cycle tree graphs. So a cycle tree graph is a cycle that you have trees that are attached to the vertices. And in this case, we do allow a vertex on the line, because it's like 3 of order 0 that comes out of it. So this we are already covering quite a lot of the graphs, and maybe very close to exhaust the geometric free, the conjugation free geometric presentations. And we proved that if this is the case, then the fundamental group of the complement has a conjugation free geometric presentation if there are only disjoint union of cycle trees. The idea of the proof in this case is to add a line which doesn't pass through a new cycle, and this preserves the conjugation free property that was before. But the proof is rather heavy. It uses a word solvability problem, which it's a big problem in. It uses logic techniques also, and the Gaussian monoid and presentation of semi-groups, so it's very algebraic. What we use for the computation of fundamental groups is the Braid monodromy and Enrico van Kampen theorem. The Braid monodromy for line arrangement, the first one was, the algorithm was introduced in 1988 for line arrangement, but Enrico van Kampen theorem is from the 30s, and it gives you from the Braid monodromy a presentation of the fundamental group. So our Braid monodromy approach to the fundamental group, which is not necessarily the approach of other groups working on line arrangement, is deducted from our topological Braid model and Braid monodromy techniques for singular curves in general, not only for line arrangement. We turned out to have a high leverage over the pure algebraic approach. And I started with Moshe Zon here in the Institute 30 years ago, and then continues over the years with many of my students and postdocs and co-authors. So this is what we use the Braid monodromy for fundamental group, for isotopy, for invariant of embedded surfaces, diffeomorphism type, modular space, and cryptography. I find the Braid monodromy techniques very good for the line arrangement because Liebgober proved that the Braid monodromy also determines the lattice. So this gives the Braid monodromy another leverage in using fundamental groups when you talk about line arrangement. I should also mention, even though I'm not using it in the consequence, I should also mention two results regarding to Braid monodromy and to arrangements is Salvetti, the cell complexes, and Liebgober, the two complex associated to Braid monodromy. And there is generic direct algorithm for fundamental group of line arrangement that dedicate to a group of people, which I write down here. Some of them are already mentioned. So I'm coming now to the third section, which is the motivation to my work on line arrangement, and this is the classification of algebraic surfaces. We do have application of line arrangement to graph theory, to networks on the internet, to electro-optic communication, and even to epidemiology. I have a former student who's now a postdoc in School of Veterinary in Oxford. So because it's spread of disease. But our original motivation came from mathematics, and in particular from algebraic geometry, and more in particular, complements of singular curves and classification of algebraic surfaces. So we try to find new invariants for surfaces in comparison to the classification of curves. So the classification curve is very classic. It's going back to the Italian school in the 19th century. And if we have a curve, if you regard it as a topological two-manifold, it has a topological invariant the genus. And we know that every positive integer is the genus of some algebraic curve. And we know that the genus determines the topological type completely. We also know that the moduli space of all the curves with the same genus has a structure of an algebraic variety. And if you look at its closures, it's projective, non-singular, irreducible variety of dimension 3G minus 3. So one wants to or try to answer the same questions for surfaces. So can we generalize the above result to surfaces? Of course, it's not immediate generalization. When you regard X, a surface, as a topological four-manifold, it has the following topological invariants. It has the C1 square and C2, the Chern classes, which are positive. But there are other equations, other constraints. So not every pair appears as the Chern classes of algebraic surfaces. The Chern classes satisfy these two relations. The positive, I said before, and then this one and that one. This Bogomolov-Miyaoka-Yau inequality is the proportionality line that is under the proportionality line 3. Wolff-Persson filled up almost every pair in a legitimate region, but still the Chern classes do not determine the topological type completely. You also need the parity of the intersection form and the homotopy type. I just say it in general because to the same motivation, so I don't say what everything is. And in 77, Gieseker proved that the modular space is quasi-projective variety. It is well known that that for two surfaces of general type with the same Chern classes, if X1 is a deformation of X2 in some smooth family, then it is diffeomorphic to each other, homeomorphic to each other, and homotopic to each other. This just comes from the definitions, almost from the definition. So, but our original question was how to distinguish among surfaces lying in the same connected component. Assume the surfaces are given in the most straightforward way, like equations. And how to decompose the moduli space of algebraic surfaces to connected component. And later, to find new invariants of four manifolds, which are finer than the diffeomorphism type. To find surfaces which are diffeomorphic and not the formation of each other. And to find out, is there another invariant between diff and def? And this is still under work, this trying to distinguish between diff and def with another invariant. I'm not sure I would need it later. I mean, I know I don't need it later, but this question of diffeomorphic, not deformation, was solved by Manetti. And then later other examples by Catanese and Kulikov. So our original idea to attack this problem was to use fundamental group of complements of branch curves. So if we have a surface X, which is embedded in a great CPN, and then we take a generic projection, and we get a branch curve. A branch curve is the curve where all the problems are there. So the surface is generated in most places. It is, let's say, the same dimension of fiber, etc. So, and we look at the fundamental group of the complement of the branch curve, the affine complement and the projective complement. And not much is known about these groups. It's computationally difficult as the equations are not known and difficult to determine the singular points, the nodes and the cusps. So we have an algorithm that we work accordingly when we attack the problem of these fundamental groups. And I remind you that the equations are not known. And it's not really algorithm in the sense that it has what to do, but it's a plan. First, you do the Braid monodromy factorization of the branch curve. Then you use the Van Kampen theorem that determines finite presentation from the Braid monodromy factorization, then invariance property of the Braid monodromy, which are geometric invariance property. Then you have to study the quotient of the Braid group and B and tilde group. This is action of groups. And almost solvability theorem, inducing the necessary short exact swing sequence. So this work was done, the D, E, and F was done many times with people specializing in almost solvable groups. But also already the first step, computing the Braid monodromy factorization of the branch curve, can give rise to a new invariant, the Braid monodromy type. What is the Braid monodromy type? Braid monodromy is a refinement of a classical monodromy. So I used the word Braid monodromy a few times here without saying what it is. But it is a refinement of the classical monodromy. So what is the classical monodromy? Is a homomorphism from the fundamental group of the horizontal line to the symmetric group of the vertical line. So it's defined, first of all, we have to have a curve, and then we have to choose a projection. And there is at most one singular point in the projection. That's how we choose it. And we choose a point, U, which is a good point, that there are M points in the fiber. These are the bad points that do not have M points in the fiber. Let's say the degree of S is M. And when I say fundamental group here of the horizontal is fundamental group of C1 minus the bad points. And the symmetric group, the points that I'm talking about, is the intersection of the curve with the horizontal projective line. When we talk about, I say that the Braid monodrome is naturally defined. If we have a line, if we have a loop here, we lift it many times. So every loop, when it's lifted, it goes to one, it starts in one of the points in the fiber and ends in another point of the fiber. Another loop might start and ends in the same point, but this gives us some kind of a change in the endpoints, which are the intersection here. So it gives us an element of the symmetric group. And but when we go to Braid monodromy, it's almost the same. It's from the horizontal punctured disk to but instead of going to the symmetric group, we're going to the Braid group. And it's defined on the same object, on the projective curve. We have a projective curve, we choose a projection, we have the M points, and we choose a point far away from the bad points. And we are lifting in the same way, but instead of CS, we have BM there. And it's naturally defined. Every loop downstairs is brought up to some loop upstairs. But before, we only cared about what happens to this point. So we got an element of the symmetric group. Now, these kind of loops are projected to the vertical line and gives us also a motion on the whole disk. So the full disk is now changing with the braid, with these loops. It gives some motion of the disk, which gives a braid. So it's the same kind like the monodromy, and indeed, the classical monodromy factors through the Braid monodromy. So first we go to the Braid, and then it's like a forgetting factor. So the classical monodromy is forgetting factor of the Braid monodromy. And the BM, but we wanted an invariant. So this is the most definition of the Braid monodromy. And the Braid monodromy factorization goes back to Artin that proved that if we have a Braid monodromy and we choose a good geometric base of pi1, the same geometric base that we had before that goes only just around one line, etc., then the result, phi m, is quasi-positive, conjugated of the generators, and the product, the total of the product of all these elements of the G base under Braid monodromy is equal to the generator of the center of the Braid group. So there is also a statement here that the center is generated by one element. So this is the Braid monodromy factorizations, and there are many Braid monodromy factorizations for every curve according to the choice of the G base. For every G base that we choose, we have one Braid monodromy factorization for the curve S. And the Braid monodromy type is deduced from applying Hurwitz equivalent to the Braid monodromy factorization. So what is Hurwitz equivalent? Hurwitz move means that we take a group, Hurwitz move on a factorization is these two factorization, L1 and LM and P1 and PM are achieved from each other by one Hurwitz move if all the factors are the same, a part of 2 points. In 2 places, one of them is just change the place, and the other one is a conjugation. So if you you multiply all the Li's and all the Pi's, you get the same element, because LK plus 1 is PK plus 1, PK minus 1, this disappears. So the product is the same element. And Hurwitz equivalent is a finite series of Hurwitz move on this factorization. So the BMT invariants of curves, the Braid monodromy type of curves, we say that they are of the same Braid monodromy type if they have a Braid monodromy type factorization which are Hurwitz equivalent. I just want to show, to get to where line arrangements are coming, so I don't talk about the powerful, how powerful this invariant is and how these Hurwitz equivalents are really tricky. We proved together with Kulikov that the Braid monodromy type of a curve determines the isotopy type of a curve, and then we look at it for surfaces. Two embedded surfaces of the same Braid monodromy type if the branch curves are of the same Braid monodromy type. So from curves, we are going to surfaces. Of course, there's a lot of work here to show that the branch curve determines the surface, because if the branch curves do not determine the surface, there is no point in talking about the branch curve, about a BMT of a surface from the branch curve of the curve, from the BMT of a curve. So you probably wonder where are the line arrangements, and here finally are the line arrangements. In the computation of the Braid monodromy factorization of the branch curve, that's where the line arrangement came in. So as mentioned earlier, it's very difficult to determine the branch curve explicitly, and also to try to compute its BMF is difficult if you don't have the branch curve itself. So the idea was to compute the BMF of the branch curve without computing the branch curve itself, and that's where the line arrangement are helping. We start with the generation. In general, the generation is a process where you transfer a complicated object to a union of simpler objects. The generation of surfaces to a union of planes is of the same type, simpler object, but it contains enormous information on the original surface that waits still to be revealed. Not everything is known. So the branch curve of the generator object, because if you had union of planes, then the intersections of all the planes are lines, so the branch curve of the generate object is a line arrangement. So here where the line arrangement came. So this is example for the generation of two union of planes where no three planes meet in a line. So this is the Veronese of order 3, and these are two types of Hirzebruch surfaces. And this is the layout of each triangle represent a plane, and intersection of two triangles is a line. How do we compute the Braid monodromy factorization of a branch curve using the generation? First, we degenerate the surface x to a union of plane x0. Then we project x and x0, both of them, to CP2, where you have S and S0, their branch curves. S0, as I said before, is a union of lines. So on union of lines, we have the algorithm that I mentioned before with Moishezon to compute the Braid monodromy or factorization of a union of lines. And then we do regeneration to the Braid monodromy factorization of S. That's where the main work is. Not the main work. First the degeneration, and then here is the regeneration, going back from the Braid monodromy of S0 to Braid monodromy of S. The regeneration involves local argumentation, global argumentation, a lot of numerative. You have to count a lot of invariants there. And also the combinatorial topology of the line arrangement. The degree of the original branch curve is twice as much as the degree of S0. So twice as much as the degree of S0 is the number of lines. So from their roles in the generation-regeneration process, we developed interest, independent interest in line arrangements and combinatorics and topology of line arrangement, which is a topic of independent research to many people. So now I come to the proof. So proof of fun conjecture. So there were a few results that I mentioned before, and I decided to prove here the fun conjecture, all of them. First of all, because it was famous there, and secondly, because the other result that is very new it's now being finished by Phi, and he might come here, so maybe in some private discussion I can do that. So I recall what I said before. What did Fan prove? Fan proved that if the graph has no cycles, then the fundamental group of the complement is a sum of free group and a commutative free group. And he conjectured that the converse is also true. And we proved that if we have line arrangement which has no pair of parallel lines, then the fundamental group of the complement, of the affine complement, has the structure that Fan wanted. The move from affine complement to projective complement is just one step before, but I'm going to prove here only the affine case. We also proved the projective case. So we have to prove that the graph doesn't contain cycles. First, very trivial remarks concerning groups in general. That if you take the commutator subgroup and a subgroup which is the commutator with the group, with the full group itself, then the quotient of G2 by G3 is generated by commutators. This is a very simple algebraic statement. Simply, you play with the relations. Then you need also to notice that or to define this function with these properties, that because later you are using it in the proof, and sometimes when it's not well defined, that's where proofs are falling apart, where someplace something wasn't well defined. So this just shows that taking two elements in the abilization of G and taking the commutator and quotient under G3 satisfies these relations. So it means that the commutator here are like multiplicative from both sides. For G, which is a fundamental group of complement of line curve, I take the natural set of generators that each relates to one of the lines. I mentioned this set of generators before when I talked about conjugation-free presentation of fundamental group. So when G is actually the fundamental group of the line arrangement, it's easy to calculate G2 over G3. It's a implementation. The implementation shows you that, as before, it's generated by the commutators, but the commutators are those that are related to the very simple geometric presentation that we take here. And the relations are, this is the relation of the change of the commutator, and then commutative of the commutators, and then the product. This is the main relation that we work with later. But these are all the relations. We can use the following generic presentation of fundamental group of complement of line arrangement that has this kind of cyclic relations. But unlike before, that it was conjugation-free, the SI were ones everywhere. And in this case, it's still cyclic, but the conjugation is not one, it is S. It is something. So this is the when it's a generic presentation, when it is conjugation-free presentation, it means that all the SI are one. It's important to notice that the cycle relations that were used here and also in the conjugation-free relations are equivalent to commuting relation. Each of the elements that appear in this cycle commutes with the product. And of course, because the product is the same, it commutes with all the products. Because when two lines meet in one point and two other lines meet in another point, and they don't, and the points do not, and there is no line that in both points, then the relations are, there is no relations between the two lines. In that case, it means that for line arrangement, we can present the group G2 over G3 as direct sum of CP, where every CP is the same group as the big one, but relates to the lines that meeting in one point. So CP is looks the same way as G2 over G3, but only for lines that meeting in the point P. We have to work out the stabilizer of X in the abilization of G. The stabilizer relatively to the conjugation is those that Fyx equals E. So it means that it is stabilizer in respect to the conjugation. And if G is a fundamental group of the complement of line arrangement, this was in general for every G. And if G is a fundamental group of complement of line arrangement, then when we take an element, the element can be the element that appears in the fundamental group presentation that we talked about before. So we start with, for line arrangement, we start with the multiple points. There are Li1 to Lim lines passing through this point. And these are the generator that relates to each of these lines, the generator that goes around the lines, be the related generators of G, and Xi goes to G, be the conjugate that appear in the related relation. So we have this relation. Now we take this element, gamma I1 X1 to gamma I Xm, this is MQ, and the stabilizer of the point Q is the stabilizer of this element in G over G2. And the theorem here that if Q is an intersection point, then it gives some presentation of the stabilizer of the point. One direction is deducted from the decomposition of G to direct sum of subgroup, as I said before, according to the multiple point. And the other direction can be deducted from the fact that the cyclic group relations are conjugated relations related to all lines through Q, and it's equivalent to the commuting relation that I showed you before. So these are the main 2 points that you use for this. And of course, it might be fun for some people, less for other people, to demonstrate it on small examples. So I took 2 small examples, one with a cycle and the other one without a cycle. I will leave the cycle, the one that has no cycle, and I will look only the one that has the cycle. So if, for example, I look at the point Q, then it's induced relation CBA equals BAC equals ACB. We don't have conjugate in this case. So MQ is CBA. And then one can show that C commutes with CBA in the quotient. And therefore, the C belongs to SQ, the same for AB, and we have the one side. And the second side is playing with the relation in G2 and G3, and without using here, we don't use almost any geometry, with just what we know already on the algebra. We need the uniqueness theorem for a general G. So we start, when we have this construction that the group is a sum, and we want to have some geometric property. So usually it's easier to go from geometry to algebra. Here we go from algebra to geometry. So we start to deduct from the anatomy, from the structure of the group, I say to physiology, to projections. First, any projection relate to the natural projection to one of the 3 subgroups, and secondly, the simplification of the projection of the kernel. So the first one is just this theorem is for any group. If you have a sum like that, if you have a presentation of a group like that and a projection, then the projection must pass through one of these components, through one of these AI, when you have a free group here and a commutative free group here. The resultant theorem for line arrangements uses also the stabilizer theorem that we had before. And what we get here, I do it a little faster, what we get here is that when we have lines passing through a point Q, and we take this product which appears in the relations of this multiple point, Then we take the normal closure of this point and the lines that do not pass through the multiple points. C is a complement. They do not pass through the multiple point. Then if we take the quotient, we are coming to a free group. And the G becomes the semi-direct product, and there exists a projection that gives exactly what we want in H and in N. So this is the way where it is when you have multiple points in the line arrangement. You need a better fine analysis of the line arrangement behind the projection, and because you want to know not only we know that this is the case, so it's not enough to know that it projected through A. We want to know that a line which doesn't pass through the point then will disappear only these projections and become the identity. And more important, that every AI is achieved in this way for some multiple points. So each of these AI is for some multiple point. And then we get a corollary that if the group, if P1 to Pm are the multiple points, then the group is the sum of Ci plus B, where Ci are free group related to the number of lines that meet in Pi. B is still not, we don't know what B is yet. And the main result is that if we have a line arrangement which has no pair of parallel lines, then if it is a sum of, if it looks like what we want, this is free and this is free commutative, then the graph has no cycle. This is a fine case, and the projective case can be deducted using Oka's result. Assume to the contrary that there is a cycle, and we choose the minimal one with R, that only R points are involved. We receive the contradictions when we take equations. So the R point that participate in the cycle, each of them has Ni minus 1 lines participating in each cycle. So this is the maximum of lines that we have that participating in the cycle. These are the generators, and these are generators that do not relate to lines that do not pass in the cycle. So we look at H. H is the group when you take the group and you quotient with the lines that do not appear in the cycle and the product of everybody. Then it's like removing all the lines which do not participate in the cycle, and the multiplication of generator of the lines are in the cycle. So on one hand, we have that the rank of H is smaller than B minus 1, because B is the number of lines that appear. So these are the number of generators, so it must be less than B. On the other hand, by the previous theorem, we had some kind of a presentation that we came, and we know that each Ci is Fn I minus 1 and plus B, but we don't know that this B is necessarily abelian, because it might have also some parts from the subgroup that do not come through the cycle, from the other parts, from the other graphs. But anyhow, we have here some B1. And we know that the projection that takes N goes to the identity. And we know that Ci over N is the free group. And when you take quotient, it's like abelianization, so it becomes Z to the power of Ni minus 1. So if you take quotient of this statement, then you get this statement, quotients first by N and then by Z3 in general. And it turns out immediately that the rank of H is greater than B. So we get a contradiction, and I proved one theorem almost full as I promised. And this should be the end if I don't go to the animation, but I don't think that I have time for animation. But you will tell me if I have time or not. It's
but let's thank the speaker.
Okay.
Maybe if anybody wants to stay for the animation.
No. Logical model for the Braid group Bn. If D is a closed disk and we have N points in the closed disk, So the Braid group is the diffeomorphism of the closed disk that are identity on the boundary and keep K in place. So the Braid group is the group of diffeomorphism with the quotient by the action on the fundamental group. Naturally, if you have a diffeomorphism that fixes the finite points, it will also induce a homomorphism of the fundamental group. A G-base is a very fundamental element that goes like this, like this. All the G-base, the geometric base around the points, are going around, are very simple loops around each of the points that don't touch each other. And a half twist, I don't go into the formal definition, a half twist in the very simple case is simply 180 degrees that brings -1 to 1 counterclockwise and then goes from the semicircle to the end it goes slowly till it rests on the outer circle. So this is a half twist. And the half twist induced by C, I take the subtubular neighborhood of the curve. I take it here. I have here the line between these 2 points goes here. It's important not to me. This is a hole, so we cannot have it. We do 180-degree rotation here, slowly till it rests on the boundary, and we come back. And the definition of the Braid group, and in the Van Kampen theorem, we need the action, the natural action of the Braid group on the fundamental group. And this is something that you do a lot of times. And this is the animation that I want to show you, how the simplest loop acting on, how the simplest braid, half twist, acting on the simplest loop. So if we have here, this is the loop that we have. The loop starts from one point, doesn't go, these are holes, the black are holes, so it doesn't go here, and comes up to 2, 0. It stops a little bit before 2, 0, takes a circle counterclockwise and goes back. So it's enough to have a path, but it represents a loop. Now here we have the semicircle, here we have the half twist that turns out these 2 points to each other. In the blue circle, it goes counterclockwise, it goes 180 degrees. From here, the degrees start to go less and less till they rest on the green line. So on the green line, it becomes 0. And then, so when this half twist is acting on this loop, this point, for example, should not move, because here it's supposed to be 0. While this point here should go 180 degrees, it should come here. So I leave this here that doesn't move, and we see what happens to the point on the blue line. The point on the blue line stays like this, made 180 degrees. Now I don't need the blue and the green anymore because they just help me to make sure that I make no mistake. This looks very strange, but we are on a homotopic world, so we can make it much simpler. So this is the end. That's what we start. That's where we started, and this is what is the end. And of course, we can make it like a continuous move using the PowerPoint definitions. And this is the graphical. This is the last element, how it comes. This is how to do it in algebraic case. I will not do it, and that's it. This is the final end. Thank you.